Welcome back. Okay, today we are looking at something that literally trips up thousands of students every single year, but honestly, we're going to completely demystify it right now. We're diving deep into Boolean logic, specifically targeting the Cambridge Computer Science syllabus. So, whether you're tackling 0478, 0417, 2210, or 9618, this explainer is absolutely for you. But listen, we aren't just going to sit here and memorize dry facts today. No way. We're adopting a completely different mindset. We are going to think like a chess grandmaster. Think about it. A grandmaster doesn't just stare at the one piece right in front of them, right? They're thinking 5 moves ahead. They anticipate their opponent's next mental move before it even happens. And today, your opponent is the Cambridge examiner. To get those top-tier marks, you need to anticipate exactly what they're hunting for on that mark scheme. We're going to totally transform the way you look at logic gates, truth tables, and those massively complex logic circuits. Because by the end of this session, you won't just know the correct answers, you'll know exactly how to display your logic on the page to guarantee maximum marks. So let's jump right into this.
Here is exactly how our strategy is going to unfold today. Part 1, the primitives. Part 2, the blueprints. And finally, Part 3, the examiner's mind.
Starting off with Section 1, the primitives, the core building blocks.
All right, let's get our foundational definition locked in. Electronic circuits inside our computers, our solid-state drives, all our controlling devices, they are made up of literally thousands upon thousands of logic gates. It's like a giant puzzle. These gates basically just take binary inputs, your classic zeros and ones, and they spit out a single binary output. And when you start connecting them together, boom, you've formed a logic circuit. Now, to actually prove what that circuit does in every possible scenario, we use something called a truth table. You can think of a truth table as just an exhaustive list. It literally maps out every single possible binary output for every combination of inputs. So if you've got 2 inputs, you're looking at 4 possible combinations. If you have 3 inputs, that scales up to 8 combinations. It is pure, absolute mathematical certainty. There's no guessing involved.
Now, notice how visually distinct these foundational gates actually are. We've got not, and OR. Let's tackle the not gate first. It's that triangle shape with a little tiny circle at the very tip. The absolutely crucial point here, and this is straight from the Cambridge syllabus, is that not is the only single input gate we ever deal with. It just reverses whatever you feed it. If input A is 0, output X becomes a 1. Simple as that. In Boolean algebra notation, you'll usually see this written as the letter A with a solid bar straight across the top. Moving on to the AND gate, you can always spot this one by its flat back and that curved sort of D shape on the front. The rule for AND is super strict. Output X is a 1 if and only if both input A and input B are a 1. In Boolean algebra, we represent this specific operation with a dot right between the letters, like A dot B. And then we have the OR gate. It's got that curved, almost shield-like shape coming to a sharp point. This one is way more forgiving. The output is a 1 if either A or B or both of them happen to be a 1. Literally, the only time an OR gate is going to output a 0 is if both inputs are 0. In Boolean notation, you'll see this represented by a standard plus sign, like A plus B. Real quick before we escalate to the complex gates. Before we continue, subscribe to our YouTube channel, Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now.
Okay, let's level up to the complex gates, NAND, NOR, and XOR. Think of NAND as basically just an AND gate that has a NOT gate bolted right onto the end of it. You can clearly spot the D shape of the standard AND gate, but it has that little inversion circle stuck on the tip. So instead of being super strict and only outputting a 1 when both inputs are 1, a NAND gate is essentially the complete opposite. It outputs a 1 in literally every single scenario, except for when both inputs are 1. NOR follows that exact same logic. It's just your standard OR gate, but again with that NOT inversion circle at the end. This means it only ever outputs a 1 when neither A nor B is a 1. If there's even a single 1 hiding anywhere at the input, that NOR gate just shuts right down and outputs 0. Finally, we hit XOR, which stands for exclusive OR. This is the one with that very distinctive double curved backline. The XOR rule is highly specific. The output is a 1 if input A is a 1 and input B is a 0, or if input B is a 1 and input A is a 0. Essentially, one or the other can be a 1, but definitely not both. If they are both 1s or if they are both 0s, the output is always 0.
Moving on to Section 2, the blueprint, building a logic circuit.
This step-by-step process we're about to walk through is exactly the blueprint you need to execute in the actual exam hall. Imagine getting this plain English problem statement.
A safety system uses 3 inputs to a logic circuit. An alarm X sounds if input A represents on and input B represents off, or if input B represents on and input C represents off. Okay, don't panic. Step 1 is just identifying the states. On simply translates to a binary 1. Off means we need to use a NOT gate to invert that 1. Step 2 is writing out the formal logic expression. We are literally just translating that English sentence directly into logic. So X equals 1 if A equals 1 and B equals not 1, or B equals 1 and C equals not 1. Step 3 is where you sketch out the circuit precisely as you've written it, without trying to simplify anything yet. And finally, step 4 is proving your blue part actually works by mapping it onto a truth table. Let's see this exact blueprint come to life.
This perfectly illustrates the complete blueprint. Let's actually trace the logic circuit together. Looking at the top branch, it handles the very first part of our expression. A is 1 and B is not 1. You can see input A flowing straight into an AND gate. But notice input B. It goes through a NOT gate first, getting inverted, before it finally hits that exact same AND gate. Now look at the bottom branch, handling the second part. B is 1 and C is not 1. The line from B splits off, completely bypasses the NOT gate, and routes straight into a second AND gate. Input C, meanwhile, goes through its own NOT gate first, and then flows into that second AND gate. To wrap it up, the outputs from both of those separate AND gates feed straight into a final OR gate to give us our ultimate output X. Now, shift your attention to the truth table. Notice those specific columns labeled intermediate values? This right here is the game changer. This is exactly where students jump from just barely passing to totally excelling. The table doesn't just jump from A, B, and C straight to X. It specifically shows the calculated values for the 2 bracketed sections in our expression. Calculating those middle steps, it's your safety net. It completely ensures you don't make some silly mental math error when calculating your final output X. Stop scrolling. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions.
Let's dive into Section 3, the examiner's mind. This is our exam mastery workshop.
Okay, I am going to walk you through 2 different sample answers for the exact same exam question. One of these secures top marks, the other completely fails. We'll call the student who wrote the top answer Alex. Alex is our strategist. And we'll call the student who wrote the failing answer Sam. Sam tends to rush things. I want you to critically analyze these 2 approaches. Can you spot the exact flaws that cost Sam the grade? Let's take a look.
All right, the prompt for both Alex and Sam was to complete the truth table and draw the actual circuit for this expression, X equals A and B or not B and C. This is a massive 8-mark question. Take Alex's high-level approach first. The layout is just incredibly neat. Up in the truth table, Alex has explicitly drawn out those working space columns we talked about for A and B and not B and C. Every single 0 and 1 is crisp, clean, and undeniable. And the logic circuit drawn below, beautifully spaced out, the symbols are drawn perfectly to standard, and all the connecting lines meet at precise, clear, right angles. Now compare that to Sam's low-level attempt. The working space in the truth table is totally, completely blank. In the final output column, look at row 4. There's a number scribbled out, and it is honestly impossible to tell if it's supposed to be a 0 or a 1. And the circuit drawing? It's a bit of a disaster. The lines are crisscrossing and overlapping in a super confusing way. But there's a fatal flaw in the actual gate Sam decided to draw. Do you catch it? Let's see what the examiner had to say.
Here is exactly what the Cambridge teacher noted in red pen. Alex's high-level answer locked in all the marks. Because those crucial intermediate stages were included, the final column was flawlessly clear, the correct standard symbols were used, and importantly, all the gates had 2 inputs or fewer. Sam's low-level answer, on the other hand, just hemorrhaged marks. The teacher's grading notes are brutal, but they're fair. That final column in the truth table, it's marked incomplete. That scribbled alteration on the 4th row is totally ambiguous. Listen, examiners are not going to guess your intentions. If it's not undeniably a 1 or a 0, it's just marked wrong. In the drawing, the connecting lines are a tangled mess. But the absolute worst part is that Sam actually invented a totally non-standard OR symbol. And for the bottom AND gate, Sam actually drew a 3-input AND gate. Remember our core rule? In the IGCSE syllabus, all gates except for the NOT gate are strictly limited to a maximum of 2 inputs. Sam tried to force 3 lines into one single gate, which completely violates the rules of the syllabus.
So, what does this all mean for us? Here is your ultimate blueprint for exam mastery.
If you want to absolutely guarantee top marks on these Boolean logic questions, you have to internalize these 5 rules, pulled directly from examiner feedback. Number 1, always use the intermediate working space columns in your truth tables. Work out those bracketed sections first. Don't skip steps. Number 2, use the exact standard syllabus gate symbols. Absolutely no inventing shapes. A D shape is AND, a curved shield is OR. Stick to the script. Number 3, draw your connecting lines with care. Use right angles whenever you can. Never let lines cross in a way that creates ambiguity. Number 4, look, if you make a mistake in a truth table, it happens. Completely crossed out the incorrect 0 or 1 and write the new value clearly next to it. Ensure it is perfectly, undeniably legible. And number 5, never ever use more than 2 inputs per gate. The only exception is the NOT gate, which only ever takes 1 single input.
We've journeyed all the way from the simple primitives up to complex blueprints, and finally right into the strict mind of the examiner grading your actual paper. So the question is, are your logic building blocks ready to withstand the examiner's test? The next time you sit down and face a massive, complex truth table or some tangled circuit problem, don't just act like Sam and rush to scribble an answer. Think 5 moves ahead. Use your working columns. Draw clear, precise lines. Be the grandmaster. Students who implement these computer science strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly explainers. Here's your final reminder. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to @acetheexams_IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for computer science and the biggest challenge you're facing. Our team responds to every comment. Like and share this explainer with a study partner. Ace the Exams. Your Cambridge success starts here. Keep thinking ahead, and I'll catch you in the next explainer.